So, welcome to Thermodynamics chapter. The outline of this particular chapter is what is thermodynamic system and what are the different thermodynamic systems available. What is the work done by a gas, different types of processes that are involved in thermodynamics, specific heat of a gas, zeroth law of thermodynamics, first law of thermodynamics, and adiabatic process. This is the course outline for this particular topic, right? And we will start with initially what is thermodynamics, right? What is thermodynamic system? So thermodynamics basically deals with, or it is a study of exchange of heat energy between the bodies and conversion of the same of the heat energy into mechanical energy or vice versa, right? Like for example, you heat a gas, what happens? There is an increase in the internal energy of a gas, or I can say there is an increase in temperature of the gas, or there is a possibility that the gas expands when you heat it, right? So when you're heating, the mechanical energy of the gas is increasing. At the same time, when you try to compress the gas forcefully, you can see that some of the heat is being released from the gas, right? So thermodynamics basically deals with this, exchange of this heat energy and conversion of this heat energy into mechanical work. So we'll just write it down, changing the font. Deals with conversion of heat energy to mechanical work and vice versa, right? So now, in order to understand what is the state of a gas, we can understand it by three parameters of a gas, that is by pressure, volume, and temperature of the gas. These three parameters defines what is the state of the gas at any point of time, right? So based on different conditions where we have different kinds of thermodynamic system, and they are open system. So what is an open system? If there is an exchange of matter and energy with surroundings, then it is called as an open system. And the second one is called as closed system. So in case of a closed system, by the name itself, we should be able to understand that exchange of matter is not possible. That is, there is no exchange of any mass with the system and that of the surroundings, but there can be exchange of energy from the system and the surroundings. There is no exchange of matter, but there is exchange of energy. And the third one is called as isolated system. What is an isolated system? Here there is no exchange of matter as well as energy. No exchange of matter, neither energy. These are the different thermodynamic systems that we have in this particular course. Now we are going to learn about work done by a gas. How can gas do work? That is a common question that we should get. So let's say we take gas in a chamber where there is a free piston or a movable piston on the other end. Right? Let's say as of now, the pressure over here is P. Now, with this pressure, there is a possibility that I can move this piston up. Right? Let's say, and I'm moving this piston up by a distance of, delta x. Area of cross section of this piston is A. Then the change in volume is A into, sorry, let's make it as delta V for easy. So delta V is A into delta X, right? Now, how do we calculate work? Work done is generally given by F into dx. Force is nothing but pressure into area into dx. But P into A dx, or it is A into delta X, can also be written as P times of dV or delta V. This is the work done by a gas. Right now, in different graphs, you can calculate the work done. Generally, if you have a pressure and volume graph like this, where volume is on x-axis, pressure is on y-axis, and let's say the graph is somewhat like this. And if I have to calculate the work done, if you look at this equation, this basically represents area under the PV curve with v-axis. Right? That means this is the area. This represents integral P dV from V1 to V2. This can be called as the work done by a gas. And remember, if volume is increasing, that means you say that gas is doing the work. On whom? It is doing the work on the surroundings. If volume is decreasing, then the work is done by the surroundings on the gas. This is something which we have to remember. So you can make a note of it. That is, if dV is positive, work done is also positive. If dV is negative, then work done is also negative. Right? The next concept is different types of processes which we see or which we come across in thermodynamics. They are, we'll first note down each of these names and then we will go in detail about all these processes. Right? So the first one is isothermal. Second one, isobaric process. Third one, isochoric process. Fourth one, cyclic process. First, we will start with isothermal. Isothermal, the name itself suggests that temperature is always constant. If temperature is constant, then delta T is always 0. Right? Now we will see what happens to the other parameters like pressure and volume if temperature is constant. Let's start with the ideal gas equation, PV equals to nRT. If temperature is constant, the right side part is always constant. Right? If right side part is always constant, I can say that P into V is always constant. Right? This is also called as a Boyle's law, and the graph between pressure and volume is going to be like this. Right? Now, what are the other important aspects of isothermal process? Internal energy, delta U, is given by NCV delta T. Right? This is the formula for potential energy or change in potential energy. Right? If delta T is always 0, delta U has to be 0 in an isothermal process. There cannot be any change in this. As long as temperature is constant, the potential energy of the gas or the internal energy of the gas will always remain constant. Right? Now, the next thing that we are going to deal with is the work done in case of an isothermal process. Work done is generally calculated by integral PdV, but we have PV equals to nRT, or pressure is nRT by V. Substituting that, we have nRT by V dV integral from V1 to V2, which is nRT into ln of V2 by V1, or the same thing can also be written as P1 V1 equals to P2 V2, because PV equals to constant in an isothermal process, or V2 by V1 is nothing but P1 by V2. Substituting that, we have nRT into ln P1 by P2. This is the work done in an isothermal process. Right? These are the main aspects of isothermal process. One is work done. You should know the formula for work done no matter what. That is nRT into ln V2 by V1, or nRT into ln P1 by P2. And internal energy of a gas always remains constant, and PV equals to constant. These are the main aspects of isothermal process. Right? The next kind of process is isobaric. Isobaric means pressure is constant in the gas. When pressure is constant in the gas, what happens to the ideal gas equation? PV equals to nRT. V is directly proportional to the temperature, or if you plot a graph between temperature and volume, it is basically a straight line, because V is directly proportional to T. Right? Similarly, we can draw graph between PV and also PT, but here, since pressure is constant in both the cases, you'll get a horizontal line. So we will not deal about that as of now. Right? What about the work done? This is the first one. What about the work done by a gas in an isobaric process? It is still PdV. Only thing is pressure is constant over here. So when volume is going from V1 to V2, it is P times of V2 minus V1, or it can also be written as nRT2 minus nRT1, or which is nR times of T2 minus T1. This is the work done by the gas in case of an isothermal process. All right, next. What about the internal energy, delta U? Delta U is always NCV delta T. That is N times of CV is FR by 2, number of degrees of freedom of the gas into R by 2 into delta T. This is always there. This is the only formula for internal energy of a gas. There is no change in this. So regarding isobaric process, the important things that we have to remember is graph between V and T. This is very important. Right? And then work done, that is integral PdV, or which can also be written as nR times of T2 minus Tv, and delta U is NCV delta T, or N into FR by 2 into delta T. These are the important things that we have to learn in isobaric process, right? The next one is an isochoric process. Isochoric means delta V is zero. That is, the change in volume is zero. If there is change in volume is zero, what happens to the ideal gas equation of PV equals to nRT? P is directly proportional to T. And if you plot a graph between temperature and pressure, it is going to be a straight line like this, right? Now, what happens to the work done by the gas? That is integral P dV. Since change in volume is zero, dV is also zero. So work done by a gas in case of an isochoric process is always zero. If work done is zero, whatever the heat is supplied to the gas is used only in increasing the internal energy of the gas, right? So the dq supplied can be written as ncv dt, which is nothing but the change in internal energy of a gas, right? The next one, or the last type, is cyclic process. What is the meaning of cyclic process? We call any process to be cyclic if the gas is reaching to its original state. When I say original state, let's say a gas is having its initial parameters as P1, V1, T1. No matter whatever path or process it takes, it has to come back to its original state. That means finally it has to reach P1, V1, T1. Then such kind of a process is called as a cyclic process. Now, we can analyze few things out of the cyclic process. What is that? What happens to internal energy of the gas in case of a cyclic process? Delta U. In the entire delta U, like we have seen earlier, delta U solely depends upon the temperature of the gas. If initial temperature is T1 and if the final temperature is also T1, then delta U is zero because there is no change in the internal energy. But that does not imply that there is no work done by the gas or no heat is supplied to the gas. That we will see now in some time. Because if you take, for example, this as an example, it is going from here to here, that is, it's expanding because volume is increasing. And then here it is compressing, that is, volume is decreasing. But if you take the first area, this is the first area when the volume is increasing. Let's call it as A1 and it is positive because the volume is increasing. Let's take the second part of the area, that is this, when volume is decreasing A2 and it is negative, right? So which part is more? Yeah, so the total area is A1 plus A2, right? When you add these two, I know that the net area is negative. Net area is negative means basically it is the area under the PV curve, right? Or it is the total work done. If net work done is negative, what does that imply? It implies heat is released by the gas. Or there is a simple methodology to remember this. What is that? If the cyclic process is in anti-clockwise, then the work done by the gas is negative, or heat is released by the gas. And its opposite is if the cyclic process is in clockwise direction, then work done is positive or heat is absorbed by the gas. These are the important things that we have to remember in case of a cyclic process. What is that? First thing is the total change in internal energy is zero. And if the cyclic process is in clockwise direction, work done is positive by the gas. If the cyclic process is in anti-clockwise direction, then the work done is negative by the gas, or heat is released by the gas, right? The next concept that we have is specific heat of a gas. Unlike solids and liquids, gases have two different kinds of specific heats because we can heat the gas under two different conditions. Those two conditions are we can either keep pressure constant and heat the gas, or we can keep the volume of the gas constant and heat it up. So that's why we have two different kinds of specific heats. But first, coming to the fundamental definition of specific heat, what is specific heat? In solids or thermal expansion, we have learned, or in calorimetry, we have learned that specific heat is the amount of heat energy required to raise the temperature of a unit mass of a substance by 1 degree Celsius. Right. Similarly, in case of gases, we are going to learn something like this. We have different kinds of specific heats, but we will confine ourselves to read or to understand only certain kinds of specific heats. Right, like molar specific heat. Molar specific heat of a gas is nothing but the amount of heat energy supplied to raise the temperature of 1 mole of a gas by 1 degree Celsius. Now, this can be divided or classified into two parts because, like I said earlier, we can increase the temperature at constant pressure or at constant volume. When we are dealing with constant pressure, this specific heat is called as Cp, that is molar specific heat at constant pressure, and it is given by delta Q by N into delta T at constant pressure. And the next one is called as Cv, that is molar specific heat capacity at constant volume, which is delta Q by N into delta T at constant volume. Now, for any gas, these formulas or the value of Cv is given by Fr by 2, where F represents the number of degrees of freedom of the gas, whereas Cp is given by F by 2 plus 1 times of R. So these are just fundamental formulas that you should know. Apart from this, there is nothing much that we can learn in this, right? And some of the relations of Cp and Cv is gamma, that is adiabatic constant of a gas, is given by Cp by Cv, and the relation between Cp and Cv is also Cp minus Cv is R, that is universal gas constant. These are the things that we should know about molar specific heat capacity. So obviously, what will be the units for this? It is calorie or joule per mole Kelvin. This will be the units of molar specific heat capacity. The next concept is zeroth law of thermodynamics. What is zeroth law of thermodynamics? It's quite interesting and simple to understand as well. Let's say we have 3 chambers like this. All right. Where this is an insulated chamber, insulated, whereas this one and this one are conducting. When I say conducting, they are thermally conducting, right? And the gases present over here are A, B, C. So here A and B are in thermal equilibrium and B and C are also in thermal equilibrium. What can we infer from here? Simply, zeroth law states that if A and B are in thermal equilibrium, B and C are in thermal equilibrium, then A and C are also in thermal equilibrium.
Simple, right? Obviously, if temperatures of A and B are T1 and T1, and I say that B and C are also are in the thermal equilibrium, so their temperatures are T1 and T1. Obviously, I can say that A and C are also in thermal equilibrium because their temperatures are also T1 and T1. This is called as zeroth law of thermodynamics. Clear? The next concept is first law of thermodynamics. This is also very interesting, and it is simply based on conservation of energy, nothing else. That is, we have a gas fitted with a movable piston, and when we try to supply some heat energy to the gas, what happens? We know that the temperature of the gas increases. On top of that, even the piston moves upwards, or I can say there is work done by the gas. In simple terms, we can say that whatever the heat energy is supplied to the gas is utilized in increasing the internal energy of the gas as well as work to be done by the gas. If you put it in a mathematical form, delta Q is delta U plus delta W, right? And delta U is always NCV delta T. How? Let's take an isochoric process. If it is an isochoric process, delta W is 0, which implies delta Q is always delta U. But what is delta Q in an isochoric process? Isn't it NCV delta T, which is delta U? Since delta U solely depends upon the temperature, this part will never change no matter what kind of process it is. Delta U is always dependent upon the delta T, right? This is the first law of thermodynamics. Here we can understand that work done is positive if volume is increasing. It is negative if volume is decreasing. Similarly, for heat, it is positive if heat is absorbed by the gas. The same thing is negative if heat is released by the gas. Right? And similarly for delta U is positive if temperature increases, it is negative if temperature decreases. This is about first law of thermodynamics.